Thank you for joining our presentation today. We're going to talk about a very unique piece of equipment. I hope you enjoy the presentation. The piece of equipment is called a tube feeder. My name is Chris Close. I'm a business development manager at the TerraSource office in Duncan, South Carolina. I'm going to talk about the tube feeder. First, just to introduce it to you and the fundamentals of its operation. It is an underpile type of reclaimer. Basic principle is that there's an outer rotating tube that activates the material around the tube. That activated material flows by gravity through the slots in the tube. You can see an actual tube feeder installation in the small picture in the lower right-hand corner. Material flows through those slots. The slots, as you can see in the picture, are sort of symmetrically placed along the tube, along its entire length, and therefore there's a uniform feed of material through the tube and into the tube. Inside the tube, as you see in the illustration, there's a screw conveyor, and that screw conveyor operates and feeds the material in the illustration to the left-hand side, where there's a collecting belt conveyor that takes the material away to the process, the digester, the boiler, the whatever. And the tube, or the tube feeder, sweeps along the bottom of the pile, so it's not sitting in one location, it's actually traveling under the stored material. So it creates a live storage area under the entire stored material. Okay, one of the things that we've learned is that, and one of the things we'll talk about in more detail is, in order to give it an even reclaim and a smooth operation of the tube feeder, we like to change the tube rotation as it relates to the travel direction. And we'll talk about that in a little more detail and what the benefits are of that. So just to kind of highlight some of the features, how the machine works, why it was developed, and so forth. The tube feeder was basically designed to remove or to reclaim bulk material from a storage silo or from a storage pile. As we said before, it's comprised of the outside tube with slots. That tube is rotating, and to give you a sense of how it rotates, 1 to 6 RPM, so you can imagine that it's rotating quite slowly. The screw conveyor that's inside of the tube is running at around 20 RPM. The slots are fitted with what we call activators, which actually fluidize the material around the tube as it rotates. And again, we'll go into that in a little more detail with some graphics a little later. The reclaim rate is around up to around 300 cubic meters an hour. And for those of you to kind of give a better representation of what that is equal to approximately 100 tons an hour of a wood chip or a biomass type material. The material, as we said before, is fed into the tube and then taken away from the tube and over to the conveyor on the side. The whole unit traverses under the material, as we said before, and the tube rotation is dependent upon the direction of travel. That gives, essentially what that does is gives a more consistent flow of material into the tube based on the way it's traveling. The tube and the internal screw conveyor that's taking the material away is what we call a closed force system, meaning that there's no external forces that are have to be absorbed by the structure around the equipment. We'll talk about that in more detail with the graphic that shows it a little bit better. Material is conveyed into the slots using gravity. It's not just using strictly mechanical force as with other types of under-pile screw reclaimers. The main benefit of that being that the power consumption for this unit is can be as much as 70% less than traditional screw reclaimers. The slots are identical across the length of the tube, and this enables material to flow into the tube uniformly across its full length, and that has some decided advantages in making the reclaimed material more homogeneous, and also makes the material in the storage flow down more uniformly as it moves through the storage. We do have both linear and circular units, and the circular unit, the tube design is the slot design in the tubes is a little bit different in that the material that's drawn into the tube, the outermost part of the tube is covering more distance and therefore has to reclaim more material than the center does, so we have a slightly different slot design for that type of tube feeder arrangement. The flow through the storage system is first in, first out, which is often important. And the feed rate is uniform and is basically a function of how fast we turn the tube. So to kind of summarize, the major advantages are over traditional traveling screw reclaimers are a lower energy consumption, a better homogenized mix of material from the storage onto the process or to the boiler. There's less degradation with this type of equipment than there is with traditional under-pile screw reclaimers. So in a case where you have a pulp mill and you want to maintain the integrity or the quality of the material that you're reclaiming, the tube feeder just has a decided advantage there. And we can do precise blending of qualities. A lot of times they'll mix species of wood chips, for instance, and the tube feeder is very good at doing blending. As far as there's a significant reduction in energy cost and also wear of the equipment. There's a better process control because of this uniform feed and the homogeneous material as it goes into the process or the boiler. And there's also some investment savings of this type of equipment over the traditional reclaimers in things like the structure and foundations around the equipment, and then also the electrical costs associated with the equipment. So here's a couple of pictures to give you an idea of how the equipment looks. The circular type units in the upper left-hand corner with a turret and then a cantilevered tube feeder, and then on the right is a linear system. Another look at a linear system, but it's the same in either case. This shows the slots in the tube and then the activator, which is actually fluidizing the material around the tube as it rotates. Where these have been used in most applications, I would say that the greatest percentage of machines have been used in the pulp and paper industry or the bioenergy for the production of electrical generation, and then some in board mills. So here's a graphic of how the unit works, and also talking about the direction of travel as it relates to the rotation of the tube. As you see in the left-hand picture, if we're traveling towards the left-hand side of the page, the tube would rotate clockwise as it activates the material. And then you see when we travel in the opposite direction. So the leading edge of the tube is always turning up into the material. What this does is it helps with the consistency of the operation. The reclaim rate as it relates to the speed of rotation of the tube will always be the same. If we were rotating in the same direction all the time, the reclaim rate would vary if you were traveling to the left or to the right of the page. So if we change the rotation of the tube, it makes for a more consistent reclaim rate. It doesn't require the operator to have to change the speed of the tube. Eliminates fluctuations based on travel direction. And one of the more important features is it keeps larger pieces of material from wedging between the tube and the floor of the storage. So here we'll compare the two different types of reclaimers. A traditional, hopefully you're familiar with the traditional under-pile screw reclaimer and how that works. The screw is always working under a head of material. It is also trying to shear material above it as it reclaims material from the storage. This sets up pressure against the wall. If you see in this side over here, you see over here, as we're reclaiming material along the screw, the material up here, due to friction of material above the screw and the screw, it sets up pressure on the wall of the silo, and it also sets up thrust loads in the opposite direction as the material is being reclaimed. As the material is being reclaimed this way, there's a thrust load created in this direction. That thrust has to be taken up in the foundation. The tube feeder, on the other hand, is the thrust loads are taken up within the equipment itself. So you have material flowing in through the slots of the tube. Material is moved internally by the screw conveyor over to the belt conveyor that takes the material away. But there are no thrust loads that are imparted into the structure, and nor are there any friction load, which creates this wall pressure as you have with the screw conveyor. So to summarize those items, the inside screw and the horizontal, the reclaim of material is protected from the material pressure. This helps to preserve the integrity of the material. Tube and screw constitutes a closed force, so you don't have thrust forces and you don't have pressure building up on the walls of the silo. There are no shear forces between the material being reclaimed and the material above, which helps to reduce the horsepower or the power requirements, and there's no thrust forces. And there's a low material pressure on the tube, which means that the horsepower requirements are low as compared to a screw conveyor or to an under-pile screw reclaimer. So the technical benefits as compared to the traditional types of underpile reclaimers. There's a lower power demand. There's a lower energy consumption. Minimal wear on the screw and tube. These come into more into the operational costs of the equipment after it's installed, maintenance and repair costs and so forth. There's a consistent reclaim. This, by being able to reverse the tube in its rotation relative to the traveling direction, this equipment allows you to do that. The concept allows you to do that. With the traditional underpile screw reclaimers, the screw always has to turn in the same direction in order to be able to reclaim the material. With the tube, that's not the case. So we do get a more consistent reclaim from the storage into the processor onto the boiler. And it's capable of handling a wide range of fuels. The configuration of the slots is determined early on based on the material specification. The slots or the activators are adjustable, which in turn adjusts the slot openings so that it can be adjusted as the specification or the characteristic of the material changes. But it does allow for a variation in material. Okay. The graphic on the right again shows how the equipment is operating. As we said before, the small amount of material is being introduced through the slots all along the bottom of the stored material, and we're adding that material little by little into the tube. It's conveyed by the screw conveyor over to the discharge, so you get a mixture of material from all these different layers of material, which could have different consistencies. Could be sawdust, could be wood chips, could be a variety of different materials. So that's how the homogeneous nature of the material is achieved. It's a uniform flow because you are adding a small amount of material all along the length of the screw, along the length of the tube, sorry. And it's a consistent reclaim whether you're traveling to the left or to the right. It's independent of the direction of the reclaimer. This shows it in a little more colorful format, and also shows, as it shows the layers of material you see, and you might be getting layers of industrial waste, millwood, sawdust, wood chips, forest waste, and so forth. So these layers are then mixed. As the material from each of those layers enters into the tube and is conveyed across by the screw conveyor, it gets mixed, so you get a homogeneous outfeed or a blended material out from the tube feeder onto the belt conveyor. Capacity of the unit is a function of, obviously, of the tube RPM, the slot size, and then also the characteristic of the material that we're handling. The larger the product size, the larger the slots, for obvious reasons, and that's why you see the two different curves there. But based on the material characteristics, we would then determine what the slot size needs to be, and then from that we can determine the theoretical RPM that the screw will turn in order to deliver a certain capacity or required capacity. The unit has been tested on frozen material and also oversized material, and again by the rotation of the tube relative to the travel distance, we can deal with frozen lumps of material that The tube will break up as it forces material into the stored material ahead of the tube feeder. And then large pieces will be moved and either eventually accepted by or will enter into the tube through the slots or will be pushed ahead of the tube through the stored material. This is actually a model that was done of an installation in Japan. And it's maybe a little bit difficult to see, but it's a very unique design. It does actually have two tube feeders, both of those what we would call A-frame buildings. There's a tube feeder in each one of those. And to give you some feel for what this particular system was designed for, was 2 million cubic feet or 20,000 tons of wood chip storage. To give you a kind of a feel for the size of it, each of those storages are 60 feet wide, 400 feet long, and 60 feet tall. That's the material height in that A-frame. This is a graphic of that, but this just gives an indication of the cross-section with dimensions of that same facility. This is the actual installation, and you can see the outline of the building here as you saw in the illustration before, or the model. The tube feeders are obviously operating in this area here and here. There's two of them. And then in this case, there's actually three collecting conveyors, one here, and one here, collecting material from the tube feeders, and then that material comes down and is collected here. The reason for the three conveyors is that they're doing blending at this facility. So they're taking different species of wood chips and blending them before they go to the pulping process. Again, we saw this before, where you can see the tube feeder and how it fits into the internal structure of the storage. You can see that the slots are uniform and symmetrical across the tube. This is shows the tube, an example of the tube feeder in the material, how the material interacts, and you can see the slots and the adjustable activators. In certain cases, and in this particular case, because they're using, or reclaiming in this case, eucalyptus chips, they use a stainless steel tube feeder as opposed to carbon steel, which would be the standard for most applications. These are the trolleys and drives on either end. You can see that the drives are quite compact, quite small, relatively small compared with screw reclaimers or traditional under-pile screw reclaimers. The drives on these particular units, I think, are in the range of 30 to 40 horsepower. 30 horsepower for the tube and 40 horsepower for the screw. I can point out that the travel drive, which moves the tube or the tube feeder linear up and down these rails that you see here. There's actually two. There's one on this side and there's one on this side. It's not too easy to see. We'll have some other pictures later that show it a little bit better, but there's actually a gear rack and a pinion, you see here, which actually provides that movement of the tube feeder up and down the rails. This is just to illustrate how uniform the outfeed is from the tube feeder onto the collecting belt conveyor. And you can see that whether the capacity is high or low, the reclaim is very uniform on the belt. This is an installation where biomass has been used to produce electricity in a power plant in France. And you can see the same type of A-frame structure where the biomass is stored. What we've learned over the years is that the tube feeder is actually quite forgiving for the size of material. And when we first started building these units, we were thinking they would be used more for a more uniform product like a wood chip that you would have in a pulp mill. But what we found over time is that by properly sizing the slots and so forth, we can handle what we now today call a traditional biomass material, and the material can be quite varied in size, and you can actually handle some fairly large pieces. Another example of a biomass energy plant. A little bit better feel for the size of material the tube feeder can handle. There's some material being delivered from a truck, and you can see the nature of it is that it can stand straight up. You see in the back of the truck that the material is actually compacted and standing straight up as delivered. Again, some larger material at another installation in Liverpool. Okay. This is really only one of the ones that we had where we actually tried to show the size, but you can see in this particular picture that there's some material there that is approaching 8 inches in length, and in most biomass facilities, you're going to get material that is that large, even though the specification for purchasing biomass material might be a 2-inch minus, a 3-inch minus, or a 4-inch minus, but you always get some pieces that are larger, and the tube feeder is capable of handling those larger pieces. This is, unfortunately, we can't show videos in our webinar, but I've put this picture in because it shows how evenly the material does draw down. If you could see this running, you'd actually see this an active layer here of material being reclaimed into the tube, but the tube is just under this kind of valley that's in the material here. And you can see that from end to end that there's, or you can imagine, that there is an equal amount of material being drawn into the slots of the tube as it is rotating. It gave a good indication of that. And that is a sawmill residue being used in a pulp mill, but it's also representative of some of the biomass that we see today. Another view of the drive mechanism, this being the tail end of the tube feeder. You see the power transmission system here to the motors. There is a synchronous drive. There's actually a drive on either end. Go ahead and move over to the other side. There's a drive on, no, sorry, I can't see it in that picture, but there is a travel drive on each end of the tube feeder, and there is a synchronous drive that's used that synchronizes those motors and keeps the tube feeder perpendicular to the rails as it travels the length of the rail. So just a few minutes here on the economics of the machine. The operation, the process itself, the initial investment of the equipment, and the sustainability. The operation is is primarily the efficiency of the equipment as it operates, and by that the fact that it uses less horsepower than the traditional underpile screw reclaimers makes it a good choice from that standpoint, so the operating cost is less. From a process standpoint, the performance of the tube feeder, its ability to homogenize the material, to reclaim evenly and consistently, are the main benefits there. From an investment standpoint, the capital cost of the equipment in total is lower, that taking into account the install cost of the equipment. And then in sustainability, probably as it relates more to European installations, but there's some green incentives that the tube feeder has benefits by. We'll talk about those a little bit more here. So in terms of operation, we said before that the energy consumption is much less, can be as much as 70% less compared to other underpile screw reclaimers. The low maintenance cost is because of that lower energy consumption, which in turn relates to less wear on the tube and on the screw, so your wear cost, replacement cost of wear items is less. As far as the process is concerned, we talked about the homogeneous nature of the material. In the case of feeding biomass fuel to a boiler, if we can supply a more uniform fuel to the boiler will operate better and provide and will then have more stable combustion, which means the boiler runs at a higher efficiency. The optimal utilization of station power, we don't want to be producing power to run the equipment. We want to produce power to sell on the grid, so the less energy consumption we can have by the equipment in the plant, the better. And this goes back to the lower power consumed, and then the energy efficiency of the plant is improved with less power being consumed by the equipment in the plant. As far as the investment cost, these tube feeders generally have less structural steel required. As we said before, there's no thrust loads imparted into the structure, so the structure can be designed specifically for the for the structure around, or the silo for the material, but it doesn't have to absorb any thrust loads from the reclaiming equipment. And then the power consumption, the electrical supply savings, meaning that there's less electricity consumed. There's smaller variable frequency drives required, and the electrical cost for wiring, starters, etc., is less. So when you think about it in terms of install costs, these are some of the benefits of this equipment over the traditional style reclaimers. Energy efficiency is it does reduce the carbon footprint of a plant. The less power consumed in the plant, the better or lower the carbon footprint is going to be for that plant. There are electricity savings, and in Europe, the plants are charged for their electrical consumption, and also they do look at their emissions. So these are more things related to the European market. The economics, again, just to summarize, energy and power savings are considerable. They do improve boiler or process efficiency, whether you're talking about using it in a boiler plant or a paper mill where they're making pulp. And there is a reduced capital investment, especially when you think about it in terms of the total installed cost of the equipment. So that's the presentation. Yeah, if you got any questions, we can take them now, or if you might think of some things later on, so we'd be glad to field your questions now or later. Does anybody have any questions?
We did have one come through the Q&A. It says, do you have any installed outside without a cover over the pile? How does it perform in rain and snow?
Yeah, thank you for that question. Yes, we do. The majority of the installations that we showed were either in a cold climate. Many of them were, as you saw in the pictures, were in Japan, where for whatever reason that's the preferred method. I'm not sure why that is. Probably containment of material and dust and so forth. But specific to your question, they will operate in outdoor storages equally as well as in silos or in A-frame storages. The more from the nature of the pile itself, but the rain and or snow that you might see on a open air pile is normally dissipated through the material and would not have any impact whatsoever or effect whatsoever on the operation of the tube feeder in an open air storage pile. Any other questions? Okay, well, thank you for listening in today, and hopefully we've generated some interest. If you have any interest and would like to get more information, just get in touch with us via the website or email.